That geologists can measure the rate at which the continental plates are moving today, and they can also infer the past locations of the continents by using magnetic signal records in the rocks from the time of their formation. And this is important because as the continent shifts positions over time, the direction of their magnetic force is recorded, and its newly formed rocks also change. So many important geological processes, including the formation of mountains and islands, occur at boundary plates from continental drifts. And in some cases, two plates are moving away from one another, and in other cases, the plates are sliding past each other, which will ultimately form regions where earthquakes are common. Like we can assume that the plates are sliding past each other in areas like California because earthquakes take place all the time there. And in the last case, two plates actually collide with one another. And all of these examples can be shown when we take a look at like oceanic plates. And typically oceanic plates are more dense than terrestrial plates. So when an oceanic plate collides with a terrestrial plate, the oceanic plate will usually sink below the terrestrial plate. And when the two oceanic plates or two terrestrial plates collide with one another, violent upheavals happen, and that's when we get formations of like mountains and other things like that. And the consequences of continental drift. All right. So although like the rearrangement of geography from continental drift happens really slowly, the effects over time are really dramatic. And one reason for this is because continental drifts greatly impact the habitats of like organisms that live on those continents. And so about 250 million years ago, plate movements brought all of the previously separated continents to form one supercontinent, and we called it Pangaea, and Pangaea basically means, it's Greek for all land. And the formation of Pangaea had a significant impact on the physical environment of the organisms that live there, and it also had effect on the climate change, and it drove some species to extinction and also provided opportunity for groups of organisms that survived to thrive in new environments. And this is because when Pangaea was formed, it formed ocean basins that became deeper, and it lowered the sea level, and it also drained the shallow coastal seas. And this all took place when this happened. Marine life normally lived in like shallow waters, and the formation of Pangaea destroyed a large amount of that habitat. And inside of this supercontinent, it was cold and dry, and it was basically a severe environment for all the organisms that were there. So another impact of Pangaea can be found in the climate change that results when a continent shifts northward or southward, so getting colder or hotter, infecting the organisms that live there. And when faced with such changes in climate, organisms have to adapt to it, obviously. And the shifting of the positions of the continent are also thought to change the route of ocean currents, causing global climate to become colder and contributing to the formation of polar ice caps. Continental drift also promotes allopatric speciation, and this is basically when new species and populations that are geologically isolated from one another. That's the definition. And so basically what this all means is that like when we look back on Pangaea, we can it gives us an explanation for why we might find like fossils of one animal that lived in a certain climate in an area where the climate isn't the same. Like for example, in Brazil and Ghana, there was a fossil of a Permian reptile that was found that lived in a completely different environment than the environment of Brazil and Ghana. And it all comes back to the idea of this one large supercontinent splitting and then coming back together and splitting again. And although extinction occurs on a regular basis, certain changes cause the extinction rate to increase, and when this happens, we get mass extinctions. So mass extinctions occur with continental drift and Pangea, basically. And is this you, Sophia?
Yes.
Okay.
So on this topic of mass extinction, so if we look through the fossil record, it really shows that a majority of species that have ever lived are actually extinct. And so that's just for a lot of different reasons. And a lot of those reasons are just like the environments that they are in and a lot of the factors that do change. And so, although, like, extinction happens a lot, it happens all the time, but at certain times, if something in the environment happens, if so many animals and so many species die at a certain time, it's called mass extinction, and this dramatically affects planet Earth and what's going on. And so the real question we want to ask is the sixth mass extinction underway? And so due to human actions like habitat destruction, like we're really modifying global environments to such an extent that so many species are being threatened to extinction. And more in the last 400 years, more than 1,000 species have gone extinct. And this is like somewhere between 100 to 1,000 times worse than any other typical background rate. And so this question is a sixth mass extinction underway. It's a really hard question to ask because it's really difficult to be able to document what species are going extinct right now. And like for example, this would be tropical rainforests have lots of different species that we don't know about and that we're discovering every day. So if these species go extinct, well, would we really know they went extinct if we never knew that they actually existed? And so that's why we don't have an exact count as to how many animals are going extinct at the moment. And so such certainties like this, it makes it really hard to really analyze the full crisis. I mean, is it a crisis? When's it going to happen? But it's really clear that losses today, they're nowhere near as huge as the big 5 mass extinctions. So in the history of Earth, there have been 5 times where really large mass extinctions have occurred. And it's really obvious that like the amount of species that we're seeing today are nowhere near those numbers. But data is suggesting that a 6th, another big mass human-caused extinction is going to happen probably in the next few centuries or millennium. And so what it does is it takes a complex, a full environment, and it reduces it to like a pale shadow of itself. It gets rid of so many of the species, so many of the plants, so much of the environment. And so a big problem that comes with this is that when a species disappears, it can't come back, and so we lose that species forever. And this completely alters the course of evolution. And so an example would be what would have happened if 66 million years ago primates had gone extinct. Well, humans wouldn't exist because the living theory right now is that we developed from primates. And so if primates were wiped off the planet, the question is, would we be here? No, because they went extinct. And so the fossil record shows that it takes like 5 to 10 million years for the environment to recover after a mass extinction. But in terms of the Permian mass extinction, it took about 100 million years for them to recover. So the recovery time it's very dramatic, and it's not something that you want to deal with because all of a sudden all your environments can't thrive and they can't live, and so much isn't, everything isn't driving and working. And so mass extinctions, what they can do is they can also alter the types of organisms that we're finding in a community. And so an example of this would be like a rise in a number of predators is going to lead to an increased pressure of the amount of prey that they're looking for, and it's also going to lead to competition among predators. And then, so then also with removing lineages, you can also get rid of like advantageous features. So like sometimes species will develop some kind of feature, some kind of characteristic that's actually really advanced and really like, and it could lead to better organisms. But if that species gets extinct, well, that trait goes along with it. But what mass extinctions do is that they pave the way for adaptive radiations. And so what that means is that with the decline of one type of organism comes the rise of another type of organism. So another type of organism is not going to become dominant in their ecosystem or in their environment. And so this is why diversity of life has really like changed over the last 250 million years. Due to adaptive radiation, once again, because then what happens is that different species tend to fill different roles in the environment. And so after the big 5 mass extinctions, large-scale adaptive radiation occurred, and so different species and different animals came in and took over their ecosystems. And this can, this occurs in groups with major evolution and innovations. And so when you talk about worldwide adaptive radiations, fossils indicate that after the extinction of the dinosaurs, that's when mammals underwent drastic adaptive radiation. So prior to the dinosaurs, like the dinosaurs were prominent on life, and they were like the big animals. They were, they kind of were the leaders in a sense. They were in control. And so after they went extinct, adaptive radiation came in, and mammals were really able to kind of take control and become the more advanced species on the planet. And so proof of this is that 66.5 million years ago, before the extinction, any fossils that you find of mammals tend to be really small, and they're not really that diverse. And but then after that, like, you can tell, and so like these early mammals, they would have been really restricted because dinosaurs they would be eaten, or they would be outcompeted by dinosaurs. But after the decline of dinosaurs, you can see mammals getting more complex and mammals getting bigger. And so other examples of this would include the rise of photosynthetic prokaryotes and radiations following the colonization of land by plants. And then regional adaptive radiation. So these are just, it's basically adaptive radiation on a smaller scale, where just one animal in a particular environment is going to take control of that environment. And so an example of this would be basically like the Hawaiian Islands. Hawaii is really not considered that old. Like, their youngest island is about 1 million years old, and it's about 3,500 kilometers from the nearest continent. So that means that animals off the continent would have to drift over there. And so once an environment is forming, the animals are going to develop, and they're going to change in this new environment because it's not like their prior environment, and different animals are going to take on different roles in this environment because it's different than the former environment that they had lived in.
Okay.